All right, guys, we're gonna get started. Thanks for coming. I'm Nick. If you haven't met me yet, I send you emails and organize these. Nate over here, you probably recognize him. He's very recognizable. Today we got Jonathan Ellis, co-founder of DataStax, formerly Rotano, if you're wondering what his shirt means. I'm gonna talk about Cassandra 2.1. Just a couple of notes. Tyler, who's around here somewhere over there, is actually talking at the Austin Web Python meetup next Thursday. If you guys are interested, check that out. It's on meetup.com too. Next month.
And that's actually right here, isn't it?
Yes, right? It's also at Capital Factory?
Yeah, it is.
Yeah, so easy to find. Just come here again next Thursday. Next month, we're actually going to do a joint meetup with the Austin Java user group. So it's going to be on Tuesday, the 25th. So a little bit different, and it won't be here. I can't remember where the Java user group meets, but there'll be more.
It's up northish.
Yeah.
Or something.
It's off Burner Road.
It's on
Burner Road, just north of 183.
So it's on the meetup site. The address isn't on there yet, but I'll have it on there soon. So yeah, put those on your calendars. And here's Jonathan.
Thanks, Nick. So I wanted to start off talking about some stuff that we did in the 2.0 release series since I last spoke to this group. So we snuck in a few extra features into 2.0.1 and 2.0.2 after we released 2.0 final. First of all, though, the first set of slides I have is actually on lightweight transactions, and which I did cover last time, but I have better slides this time. I went back and I revised my diagrams to make it more clear. But if by a show of hands, who understands lightweight transactions? We'll skip it if we have a comfortable majority. Okay, so I think we can cover this productively. So the goal of lightweight transactions is to solve a class of race conditions in Cassandra that you would otherwise need to impose an external locking manager on top of to solve. And we don't like that because it adds fragility and it adds complexity, and it's actually even worse when things break, because if I have a locking manager and my client says lock this row and then the client fails, now I've got to deal with orphaned locks on top of all my other problems. So not a solution we were crazy about. So lightweight transactions lets us tackle this problem. So as an example of the kind of race we're dealing with, suppose I'm creating user accounts and my primary key is the username. So I'm using a natural key here. So in this case, I have one client who's asking, he's going to ask, does this user exist? And if Cassandra says no, he's going to try to create it. So one client says, does it exist? Cassandra says no. Meanwhile, a second client says, does it exist? Cassandra says no. Meanwhile, the first client says, okay, it doesn't exist, so I'm going to insert it. And then the second client does the same thing. So the second client is the one that is going to end up overriding whatever the first client did. But the first client has no way of knowing that. Yeah, as far as it's concerned, the user didn't exist, so it claimed it. Meanwhile, someone scribbled all over its data afterwards because of this race. So what lightweight transactions does is we have a shoot. I thought I had better slides. Okay, so I'm missing a statement. I think my text box isn't big enough because I increased the font size. The new clause here is if not exists. So if I say insert if not exists, then Cassandra is going to make that operation of checking to see if it exists and then doing the insert. It's going to make that a single atomic operation. And so this is what Cassandra gives you back when you do that. It will not, instead of just telling you, success or failure, it actually gives you a column in your results set called apply with brackets around it. So it's kind of a special internal column value that tells you whether your lightweight transaction succeeded. So the one that is successful will just get back applied true, but anyone who's unsuccessful will not only get back applied false, but it will also get back, here's the row that exists that you were hoping did not exist. And that gives you the extra information of, now you can decide what do you want to do based on that. Do you want to pick a different username? Do you want to update the existing row that's already there? What do you want to do? Otherwise, the common case is if I didn't apply it, then I would need to go and select from the database, okay, what is that row? So we're just going to throw that at you in the same result set to save you a round trip. So we built this on top of a consistency protocol called Paxus, which the main attractive thing about Paxus for us is that it's quorum-based. So I can still lose a minority of replicas and make progress. I don't need to have a master node that's up. I don't need to have even a majority of nodes in my cluster. As long as I have a majority of replicas for the partition I'm dealing with, then I can make progress. There's a good paper called Paxus Made Simple that explains it in a fairly simple language. Paxus has a reputation of being difficult. That's in large part because the author was a little bit too clever in his original paper. He called it the part-time parliament, and he wrote this paper using an analogy of a Greek parliament, and nobody understood it. So 10 years later, he tried again with a paper called Paxus Made Simple, and it's a lot more straightforward. There's a number of consequences to using Paxos. The most important one, perhaps, is at the bottom here, that we actually have to do 4 round trips for a lightweight transaction versus 1 for a normal update. So 3 of those round trips are for the Paxos machinery, and then 1 is to actually check your lightweight transaction condition. So if it's if not exists, or it's if this column equals X and this other column equals Y, whatever your condition is, we need to go and check what's the current value of that row in this linearizable transaction. So consequently, the recommendation is use this for the 1% of your application where you need linearizability, but for most of your application, you're going to want to continue to use the normal, eventually consistent operations. Christos from Netflix gave a great talk at the Cassandra Summit in San Francisco last year about how his team at Netflix learned to love eventual consistency and some of the experiments they ran to get comfortable with that and their thought process there. Yeah.
Do you use basic Paxos, or do you use like the leader elected?
Yeah, it's raw, basic Paxos. So we explicitly didn't want to have to deal with leader election and failover. So it has the same properties as the rest of Cassandra that, as long as you can connect to any replica, it's going to be able to coordinate that operation for you. So in the Cassandra terminology, your coordinator, whatever coordinator that the client is talking to, becomes the Paxos leader, and it will generate a Paxos ballot and handle reconciling with any other Paxos operations going on. So the operations are done on a per partition basis. So if I have a million operations going on simultaneously, if they're in different partitions, none of them are going to have conflicts. If they're in the same partition, then I'm going to have extra round trips as they decide who's going to go first. So, but that's actually a good point to take a quick break for questions. Are we good on lightweight transactions?
I got one quick question.
Yeah.
Understandably, the application can throw away the data that's sent back on a failure. Mm-hmm. But is there a security implication in actually getting that data back instead of just a failed state? It's actually handing back data from the existing row. Is that...
Sort of. So for lightweight transactions, you have to if you're using the Cassandra authorization framework, you need both read and write permission to perform a lightweight transaction, exactly because of that scenario that you do get the existing row back if there's if you lose the race.
Okay.
What, given that you know the overhead of Paxus, like, is this something that should be like relatively quick operation, or
Yeah.
what type of throughput? It's not a high throughput operation.
Right, and so I said that it does round trips between a majority of the replicas. So if you're deploying in a multi-data center environment, it's going to have to do a bunch of cross data center traffic for that. So it's really something that like this example of account creation, only happens relatively rarely compared to the other operations in your cluster. I mean, your choices are, when you need linearizability, your choices are, you really have to you have to either coordinate with a single master somewhere that might be in a different data center, or you have to do something like Paxus or Raft where you're going to do that kind of cross data center traffic. So there's no way around that latency penalty in that scenario. So your only option is really to minimize the places where you need linearizability. Moving on. We added something called rapid read protection in 2.0.2. And what that does is it lets Cassandra recover from intermediate replica failures. So let me show you what I'm talking about here. I mentioned, whatever node that the client's sending its request to in the cluster, we're going to call that the coordinator, and it will relay the client's request to some replica node in the cluster, which may or may not be the coordinator. So Cassandra uses something called the dynamic snitch to track how fast different replicas are responding to queries. So it will route that request to the one that's responding fastest. And then, if everything goes well, that replica replies, here's the row you were asking for, and the coordinator sends it back to the client. So the interesting part is then what happens if something goes wrong? Well, if the coordinator knows that this replica is dead before it sends out the request, it will just send that to a different replica, and it won't even send it to the failed one. But it takes 10, 15 seconds for awareness of failures to propagate through the cluster via gossip. So there's a window where the coordinator will not know that this replica is dead, but it won't be alive to respond to the query. And so what we've done in the past is the coordinator will wait around for a reply, and then it will say, sorry, he never got back to me, maybe he's dead, maybe he just had to stop the world garbage collection, I don't know what happened, but he never got back to me. And so the coordinator will send a timeout response to the client. So obviously this is less than ideal. So what rapid read protection does is if that initial replica doesn't get back to the coordinator in a typical amount of time, and I'll define what that is more rigorously soon, then the coordinator will retry, will perform a redundant copy of that request to another replica, and then hopefully that replica will reply, and everything, and the client will get the data it wanted. So how does it decide when to generate that redundant request? So it's actually configurable. So this is a graph of performance with different values of rapid read protection enabled. So this graph, this blue one here that dips to 0 is no read protection. So this is the classic Cassandra behavior from 1.2 and earlier versions. And so what happens here is that we're hitting the client with 35,000 40,000 read operations per second, and we killed one of the machines halfway through. And so with the rapid read protection, you can see how it takes a dip. It takes a dip in performance because I'm having to redo a whole bunch of requests all at once to different replicas in the cluster. And in fact, this is a 4-node cluster, so a small 4-node cluster. And you see that the performance goes down by about 25% when I kill it. So that's kind of what we expect. But without the rapid read protection, it just it basically has a pause while all those requests time out, and then it picks back up again once the failure detector has recognized that it's down. So those different lines on the graph, the different colors, here's what those are. We have 90th percentile, 99th percentile, sorry that these didn't come out in order, 75th, and always. So the default is 99th percentile. So it means that if the request from the coordinator to a replica, if that is one of the 1% slowest replies, then the coordinator will generate a redundant request to another replica. And then for 90th percentile, that means we'll do that for the slowest 10%, slowest 25%, and always means I'm not even going to bother waiting for the first request to see if it's slow. I'm just going to always do, I'm going to always make a request to one more replica than I would normally need for the consistency level that you asked for. So it's actually interesting, if you look at the 99.9th percentile latency, for no rapid read protection, the worst case latency is about 50 milliseconds, which is about 50 times the average latency. So the difference between average case and worst case is large. And if you're familiar with JVMs and stop the world garbage collections, it's probably not too shocking. But if we retry those slowest 1% of our queries, then the 99.9th percentile is cut in half to 20 milliseconds. So that's pretty respectable. If we go to retrying the slowest 10%, the latency goes down to 15 milliseconds. And then an interesting thing happens. If we go to retrying the slowest 25%, then it creeps up a bit to 16, and always goes back up to 36. So there's kind of an inflection point at which doing more retries makes it worse instead of better. And that's because if you look at it, we're hitting the cluster pretty hard. So we only have so much headroom in terms of how many extra requests we can absorb. And so when we start doing, at 25%, we've cut into our throughput, and at always, we've cut into it even more. And you can see that from the drop in throughput, where we actually get slightly better throughput at the default 99th percentile, just because we're cutting out those slowest 1% of the requests that we had to wait for otherwise, we're kind of stalling on. But then the throughput starts to go down as we start doing extra requests and start pouring more work into it. So, in my opinion, basically, as a rule of thumb, this is going to affect your latency for 1 order of magnitude more than you're configuring the request for. So, if I'm doing 99th percentile, do an extra request, then my 99.9th latency, I can expect that to have an effect there. If I were concerned about my 99th latency, then configuring read protection at 90 makes sense. Probably makes a little bit less sense to do other values out of the gate. But if you know that your application is super latency sensitive, and you also know that you have plenty of unused capacity in your cluster, then always could make sense. But I think our default of 99th percentile is a good conservative place to start. Okay, this is another feature that was in 2.0.2. We made some optimizations for how we deal with cold data. So by cold data, what I mean is data that isn't being read very frequently. So in this diagram, I have 4 SS tables, and these black and white arrays at the top are representing the Bloom filter of the partition keys that are in each of these SS tables. And so, the data in the upper left is the hottest. It's the data in that SS table is getting read most frequently, and in the lower right, it's hardly getting read at all. So what we do now is we take that into consideration, and we will adjust how much space we allocate to those Bloom filters based on how hot or cold the data in the SS table is. Because this is saying, if I'm only checking this SS table 10 times a second, it's not the end of the world if I'm less accurate with my Bloom filter, and I'll have to actually go and check the index a little bit more frequently. Yeah?
It could be index summary instead of local.
Is that what I mean?
Yes.
Damn it. My diagram doesn't even make sense now.
Yeah, it's still close enough.
So, yes.
What's the difference?
So the difference is, here's where the whiteboard's going to come in handy. So if I have, say, I have a notifications table, like the one I'm going to show you later on in my slides, and I have a bunch of notifications for a given user. So all of these rows are in the same partition, right? So they're in the JVE partition. And then I'm going to have some more rows that are in a different partition, the Tyler partition, and so forth. So what I have is in my index, I have a series of tuples that say the JVE partition starts at offset 0. The Tyler partition starts at offset 512, and so forth. And so when I go to look up a row from a given partition, the first thing I do is I consult this index to say, hey, where does that data start? Where can I find that partition on disk? But if I were to keep that whole set of offsets in memory, it would be prohibitive. It's too large. So what we do is we keep what we call the partition index sample, and I pick every 1/28th by default entry in that index in memory. And so what I'll do is I'll do a binary search on that sample, and then I'll go say, okay, I might be looking for Tyler instead of JVE, but I know that it's not before that part of the index, so I'll start seeking here because he's in my sample. Then I'll have a small amount of scanning to do. It'll probably be just one read from disk, and then I can go to the data file and find it. So, so pretend that instead of Bloom filters here, I'm talking about index summaries, because that's actually what we can save memory on. We're actually looking at ways where we can do this with Bloom filters. It's actually trickier because creating a Bloom filter is kind of a one-way operation. I'm losing data when I run my keys through the hashes to get to the Bloom filter buckets. With the index summary, it's relatively easier because I have the original data here, and I just have to figure out, okay, what can I resample from that original data to give me something that's still statistically useful but smaller. Thanks for the correction, Tyler.
So the binary search is only on the index, not the. So the primary index has every key in it.
Right.
And then we only keep every 128th in memory.
Right. So this is the index interval setting. So you might have seen that in Cassandra.yaml. That's what that is. So you can make it larger or smaller by default. And now we have a setting that says, allocate this much memory to your index summaries, and we'll allocate it the best way possible for you.
And I bet it's as efficient as a B tree, because it's about the same number of searches.
Well, it's like a B tree that has a single level, which is kind of a dysfunctional B tree.
So his request rates can go up and down? Does that get reevaluated?
Yes. So there's actually a threshold because downsampling the index is easy because I already have more data than I need, so I can resample that down. But then to increase the granularity, I have to be some factor of 2 off from where I want to be before I'll say, okay, now I'm going to go reread it from disk and recompute that. So we don't want to do that very often. So what we also use this information of how hot are each of these SS tables when deciding, is it worth bothering compacting anyone? So by default, it just, the behavior is unchanged, but you can tell it, don't bother compacting the coldest 10% of my SS tables, for instance. And then it will leave the cold ones out of size tiered compaction. Level compaction is unaffected because it's got a different mandate of, I must have only one copy of this partition per level. But with size tiered, we can just say, okay, we're just not going to bother compacting these. And even if everyone is above that threshold, we can still use it to prioritize, and we'll say, okay, if I have 15 different set of SS tables that I should compact, I'll prioritize the one that's getting read most, so that I'll cut down on the number of disk activity that I'm going to have to do, which will give me that much more capacity to complete the rest of the compactions. All right, so that's kind of our history of what we've done in 2.0. Yeah.
Sorry, before you get there, I did have a question about rapid read repair, real quickly. The percentile is per table. Are you tracking statistics at that level? Or
the percentile is per table, yes.
But what are you tracking statistics at? Because that's the problem with dynamic snitch. If you have one table that's really bad, even if you were tracking statistics across just a node, for in order to do the rapid read repair, you'd get some benefit because that query would still be outside of range. But I didn't know whether you were tracking the statistics on a per table basis. Or...
Yeah, it does break it down to that level. Yeah.
Okay.
So in 2.1, here's another graph of performance. This is another read performance. So we actually released beta 1 today. So I told them we have a meetup tonight. We've got to release it. We actually started the vote a few days ago, and timing worked out. But we did some smoke testing on the performance. And while it's good that our peak performance is a good 20% higher than in 2.0, it's very bad that it takes 300 seconds to warm up to that peak. So we've got so this is my slide that says, hey, it's a beta, right? This is not something you should be looking to put into production. Testing is definitely welcomed, but we've got some kinks to work out. That said, we've got a number of interesting features that are coming up and that are pretty exciting for when this is going to be production ready in a couple months. First of those is user-defined types. So We introduced collections back in Cassandra 1.2, which was a little over a year ago, which, and you know, they've been very popular, but one of the big asks has been, you know, I want to be able to nest collections. I want to be able to have a map of maps. I want to be able to have, you know, a list of sets, whatever. And we don't support nesting collections per se. So what's coming in 2.1 is kind of it allows you nesting collections, but it's more than that. So it allows you to create a type, like this address type in the upper left, and use that type as a column, column type in a table definition. So I can have an address here that has a set of phone numbers, and then I can use that address as a map value in my table definition. And I can nest these arbitrarily deep, you know, whatever makes sense. And so what this does now is that you have, you know, whatever your object hierarchy looks like in your Java code or in your Python code or whatever, you can just map that directly one-to-one to a Cassandra structure. So you know, we've had kind of we've been kind of stumbling towards this for a while. At first, we thought we were going to have some kind of, you know, object relational mapper for Cassandra, but it's a whole lot simpler if I can just say, hey, you know, here's my object graph, you know, or rather tree. There's no you know, cycles in this, but here's my object tree, and just put it into a Cassandra row. So so you know, if you're familiar with document databases, this is kind of a typed document database. So you get the benefits of the schema as well as the simplicity of here's my object tree, go save it. We've also added indexes to collections. So you can say create index on this tags column that is a set. And then I can say select star where tags contains blues. We actually went back and forth a little bit. Should we use the in keyword? In which case I'd write this as where blues in tags. We decided that it was more natural to use a new keyword for that. But also the other factor there is if I have a map has both keys and values. And so you might want to be asked, does this map contain the value of X, or does it contain the key of Y? So we actually have contains, and we also have contains key for when you want to ask, does a map contain this key instead of does it contain this value? So the next question is, well, if I can have indexes on collections and I can have user-defined types that have collections, can I index user-defined types? The answer is not yet. I don't know if it's going to happen in 2.1.x or in 3.0. It's easy to do for some cases, and it's hard to do for every case. We'd rather do it for every case rather than explain to people why sometimes it works and sometimes it doesn't, which is why it might slip to 3.0. Another thing that who's used counters in production? Tell me about that experience, Nate.
They don't work.
They don't work very good.
Not deterministic.
Yeah, so we've been working on redesign of counters, and I can briefly explain what the pain point is that if I have my Cassandra cluster and I have a row that contains a counter, and I want to replicate it to 3 nodes in the cluster, then the way Cassandra thinks about this internally is, my counter conceptually is I have a value for replica A, and a value for replica B, and a value for replica C. And then if an update, if someone says increment this counter by 2, and he's talking to replica A, then A will increment his partition of that counter, or his shard of that counter, and then he'll replicate that to the others. And so since each replica is only managing their own local shard, then we can have this kind of eventual consistent of increments. The problem is that implementation-wise, we actually have two ways of storing this data. We have this version which is here's the counter version vector. So by vector I mean I have these different cells in my array of values. But we can also store what we call a local shard, which isn't the entire counter context. It's just a delta. And the problem is that, well, first of all, the reason we did this is we wanted to be able to increment a counter without reading the existing value. Because that's going to, I want my performance to be fantastic for increments. So I want to just be able to say +2, +1, +1, +1, +3, not have to worry about what's the existing value. We'll figure it out at compaction time or at read time. The problem was that having these two different values means that it's really difficult to do almost anything with the other replicas. So repair gets messy. Bootstrapping, adding a new node to the cluster gets messy. I can't replay the commit log safely because it's full of deltas. And so if they've already been applied, then applying them again means I overcount. But if they haven't been applied, then not replaying them means that I've lost data. So what good did my commit log do me? So that's kind of the historical background there. So the short version of what we did for 2.1 is we said we're not going to do local counter shards anymore. We're just going to do the global shard, which means that all the extra complexity goes away. And I'm getting a little ahead of myself, but it also has some performance implications. So we've gotten rid of a lot of the edge cases. There's no, you don't need to understand counter internals to repair safely. In the performance sense, there's a lot less garbage. So I'm talking about JVM level garbage. We've had some bug reports of, hey, I'm doing a lot of counter reads, and all of a sudden my cluster went into garbage collection hell because of all the garbage it's generating. So even theoretical problems aside, there were some implementation problems with the old counters. So one of the nastier problems, I mentioned that if you're bootstrapping, if you're adding nodes to the cluster, this gets all kinds of problematic. And in fact, if you only had a single replica of your counter, then adding a new node while you're doing increments could lose some of those increments. So that's not a problem anymore. You can replay the commit log. Things that haven't changed, the API is the big one. One of the big things in fact, this is why it's taken us 2 years, is where our goals were, we have to fix the problems with counters, but not in a way that breaks application code. Because as difficult as it is to believe, there are happy users of counters out there who don't want to change things, at least in terms of their application. So we kept the API the same, average throughput is the same, and that's an important way that I worded it, by the way, so I'll come back to that. Restrictions, this means that, if you say create table, blah, 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 I can either have counters in that table or no counters at all. I can't mix them. So that hasn't changed. It's neither better nor worse. Although it may get better in the future because of some of the technical changes we're making to how we store the counters. So what this is referring to is that if I have a batch, it can either be a batch of regular updates or it can be a batch of counter increments, but it can't mix the two. So that hasn't changed either. Restrictions on counter deletes. Once a counter is deleted, you pinky promise never to use it again and never to try to increment it because it's kind of undefined behavior what will happen if you do that. Same retry limitations at a client level. So there is no, we talked about adding an API where Cassandra would give you kind of a counter increment ID that you could use to retry the increment if it timed out. And we said, let's hold off on that. Just as if you're in a MySQL database and you say set I equals I plus 1, and then you lose network connection or your machine crashes, you don't know if that happened or not. You don't know if it went through or not. Same thing with Cassandra's counter API. But internally, like I said, at the commit log level, we can definitely replay those idempotently, which actually makes a lot of things nicer internally. So the big downside, I was careful to say that average throughput is the same, but there's worse latency for updates at consistency level 1. So remember I said the whole reason we had those local shards is so I can just say increment, 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 increment without having to read the existing value. I do have to read the existing value eventually to send it to the other replicas, but I don't have to wait for that at consistency level 1, which is actually kind of an anti-pattern. And we had a number of customers where we said, okay, just stop doing consistency level 1 updates because you're building such a backlog of counter replication that it's actually causing problems internally. So if you switch to doing quorum level updates, or there's a configuration setting that you can disable it as well. I forget what it's called, but that will force it to do the reconcile and then replicate it before giving the answer back to the client. So that kind of throttles the client down to a level that Cassandra can handle. I think it's an improvement, but I can definitely see how someone would say, hey, my CL.1 increments got slower, this sucks. In which case, I have to say, I'm sorry, it sucks. It does make life better for a whole bunch of other people, but for your use case, yes, it does suck. I have to admit that. Similarly, because I'm now incrementing this before I replicate, I basically internally I have a lock for each counter partition, and so I have to grab that lock to do my increment, and then I know that no other increment threads are messing with it, and I haven't lost any data. Because I increment it, remember, I'm incrementing it before I write it to the commit log now, so that makes my commit log safe to replay. So if I'm doing a whole ton of updates to a very large partition of counter values, then I could have some lock contention there where none existed under the previous implementation. So in which case, the solution is, well, you need to find a way to split up your partitions into smaller chunks so that there's less contention. That's probably a good point to ask if there are other questions as well before we move on. Yes?
So how are user-defined types mapped to the cells in the storage engine?
That is outside the scope of my presentation today, but it's basically the same as collections.
Okay.
So if you understand collections, then it's basically an extension of that.
So you just do more work composing the name for the
Right. Mm-hmm.
For the user-defined types, how many levels do you go?
You know, as much as you have memory. So, you know, basically you know, it actually ties into Steve's question, which is that for every level, I'm basically making the storage cell and making the name of that cell larger to include kind of the path of that type. And so, you know, in the extreme cases, there's going to be performance implications because now my cell name is, you know, 16 kilobytes long because I have, you know, 800 levels of nesting. So, yeah, I mean, in theory, it's unlimited. In practice, you know, you probably want to be reasonable about it, but that's how it works.
Can user-defined types be part of a primary key?
Yes.
Yeah, I may have missed something now. Can you have a collection of user-defined types?
Yes.
Okay.
Yeah.
What determines the ordering if your user-defined type is part of your primary key but not the partition? Question.
That's a good question. We should probably figure that out.
I'll email docs.
Yes. Yes.
Used to be for collections, there's like a 64K limit to it.
Yes, that hasn't changed. But so there's this, you can have 64,000 values in a map or a set or a list. So the problem was that you could get into trouble by adding more values than 64,000, and then when you go to read it, it would blow up on you because we're not doing read before write. So how does it know that that you've exceeded the limit? So that's actually the problem. There is that's actually at the CQL protocol that we said, hey, no one will ever need more than 64,000 elements in the collection. So we used what is it, a 16-bit? No. Yeah, 16-bit value for that. So that's actually not going to be solved until 3.0, where we can represent larger values in the collection. Okay, so moving on. This one's easy. In earlier versions of Cassandra, if I have an SS table, this is what it looks like on disk. I have a bunch of components, so I've got the data, I've got the index summary, this isn't the summary, but rather the entire primary key index, the Bloom filter, compression mapping, statistics, summary. This is the summary, actually, the index summary, where once I've sampled it, I'll write that to disk so that when I restart Cassandra, I'll just read the summary into memory rather than having to resample the original index. So that's what that is. And then there's a table of contents in case there's actually ways to plug into Cassandra and add custom SS table components. And God help you if you need to write code to do that, but it's there. It's technically supported. But what's interesting here, the interesting part here is that my key space name and my table name are part of the path on disk. And so where this gets us into trouble is when you drop a table and then recreate it with a different schema. And there's a bunch of ways where data from the old schema could attempt to insert into the new schema, whether it's because a replica had some hints that weren't delivered, and it woke up and delivered those after the schema change was made, or Even there's even ways it can happen on a single node from commit log replay. So fundamentally, we didn't have a way to distinguish different incarnations of the same table that had different schemas. So the way this looks like in 2.1 is, we have a UUID associated with every table, and that's part of the path now. So kind of having UUIDs on your file system is ugly, but it's effective. So now when I drop this and recreate it, the new version of the table, even if I don't change the schema, by the way, the new version will have a different UUID, and so it will never get mixed. Windows has path name limitations. So my proposal to make Windows happier is to say that we have redundant information now. I have table name, key space name, table name, and then I also have key space name, table name in the data file. So if I got rid of this redundant information, that would recover some of our precious path name space for Windows. But even without that, what is this? 100 and something characters, and we have 250 or so to play with. That's plenty, right?
You answered it. That was question.
Yeah. So yeah, that is on our radar. I'm actually not sure if the benefits of getting rid of this outweigh the drawbacks of now. If I somehow screw up my backup tarball, I have no idea what table these come from. Yeah. So not actually sure what the right trade-off there is, but it's an option.
So you might back up on this in a later release.
So there are a bunch of third-party backup tools.
You might go back on this strategy.
Oh, no. The UUID is there to stay. The question is, are we going to keep the table name and key space name as part of the file name as well?
There's also now a flush there in the path. I didn't know if Brent will talk about.
Oh yeah, that's something I wanted to talk about. Thanks. So the other change. So we've gone from varlib Cassandra data by default, newly created SS tables. There's now a special flush directory. So varlib Cassandra flush by default, and what that is it lets you symlink that or however mount it to a different spindle. Basically, this is for people running on rotating disks. It lets you say, I have a spindle for my commit log, I have a spindle for flushing new SS tables, and then I have a bunch of spindles for compacting and storing, all the rest, the bulk of my data. And what that does is, it does two things. First of all, it reduces contention when I'm doing reads. My flushes are never interfering with the reads that I'm doing. And by extension, that means that if I'm doing heavily a workload that's heavy on both reads and writes, then if I'm running into memory pressure, my mem tables are getting large, I need to flush them out, then Cassandra assumes that when it needs to flush out a mem table, it should be able to do so fairly quickly. And if it can't because of contention on disk, then it can, in the extreme case, it can run out of memory and fall over and die. So that's something that's a scenario that we would like to avoid. And so this avoids that worst case. But even in the even aside from the worst case scenario, it does reduce a lot of contention. And the benchmarking we did showed a 40% improvement in performance when we have that mixed read and write workload. Yeah.
So what else would be there besides flush?
So we still have data.
Yeah. Okay.
So we have flush data commit log now instead of just data and commit log.
So does snapshotting now block on copying from flush to data?
No. So we'll still create a snapshot directory under the flush as well. So if you snapshot a newly flushed SS table, it's going to be snapshotted, it's going to be hard linked on the same volume, because otherwise you would have to copy. Yeah.
Just out of curiosity, is there a reason for bar dash rather than bar slash? Is it just easier to implement?
I was thinking that too.
Yeah, I mean,
because you can see it might be useful.
I mean, conceptually, bar slash 2F is a different object than bar dash 1A, right?
Yeah.
So it's not like it's a hierarchy of these are the different versions of bar, but because all of them are going to go away except one of them, hopefully, unless we have a bug. So I think it makes more sense with the dash, but I don't know. The bike shed has of the right color, right?
Can you tell, assuming that you do end up with multiple of them, as in, I've hit the problem where you delete and recreate even without changing the schema. If there were two sticking around for some reason, can you tell which one is the latest other than by date? Yeah.
That's like a version 1 UUID, so it has a timestamp embedded in it.
Okay.
So do that too.
Yeah.
Assuming you didn't do something really bad and create a new version from earlier in time or something. I'm not going to promise that that's always accurate, but yeah, it should. Yeah, deep in Cassandra's internal system table, it knows which is the the current one. So you've got that going for you as well.
So is it compaction then that copies from flux to data?
Yes. Okay, so we talked about Bloom filters, and this time we actually are talking about Bloom filters. One thing that's been a minor but nagging problem for 5 years now has been that if I'm compacting two SS tables together, I know that I'm going to need to build a new Bloom filter for the partitions in that combined merged SS table. But I don't know whether it's going to look like this, where the SS tables mostly overlapped, or like this, where the SS tables mostly did not overlap, or something in between. So the problem is that with a Bloom filter, it's not really resizable, which I mentioned earlier. So I have to guess before I start creating it, I have to guess what the appropriate size is going to be. So we basically say, we basically take the worst case scenario and say, let's create it with the maximum size that we'll need, which means that sometimes we'll end up with wasted space. We could be wasting up to twice or up to half of our space, depending on how much they overlap. So what we do is we use a cardinality estimation technique called hyperloglog. And that lets us have a summary of each SS table that's about 10 kilobytes large. And that lets us, we can actually combine those summaries and say, how much did they overlap in the new combined summary? And we get to within about 5% accuracy with a 10 kilobyte summary, which is a pretty good trick. So we don't keep those 10 kilobytes in memory all the time, because we can have ridiculously large numbers of SS tables as disk capacities continue to increase. But we'll go ahead and read that in. Once we've decided these are the set of SS tables that I'm going to compact, I'll go read in those summaries and use that to decide how big the Bloom filter should be. Now, this opens up some interesting possibilities, not just for Bloom filter sizing, but because what if instead of just compacting based on how large my SS tables are, which is what we do for size tier compaction, what if I could combine, I could use those cardinality estimates and say, oh, hey, look at these three SS tables overlap, with 90% of their data. So let's pick those as my compaction candidates, even though they're kind of different size tiers. So this compaction strategy is, this is the only vaporware in my talk today. We haven't actually written this, it's on paper, and we actually have someone who's interested in writing the code, but it hasn't actually been written yet. So vapor, but interesting vapor, I think. We've also, this is a bigger nagging problem that we've had for 5 years with more important implications, I think. So when you go and repair a set of replicas, we're really good at being network bandwidth efficient because we take the data in the table that's being repaired and we build a Merkle tree out of it, which basically, it's down at the leaves of the tree are hashes of a set of partitions, and then we take those leaves and we combine them into a parent node, and we rehash those 2 hashes, then we rehash those parent nodes together. So we can just ultimately, the replicas send those trees to each other, and then they compare the roots of the tree and say, hey, are the roots equal? If so, everything's perfectly consistent, everything's perfectly in sync, everyone has exactly the same data. But if they disagree, then we can logarithmically, we can look at the left half and the right half and say, okay, do they disagree because of problems in the left half or because of problems in the right half? And so every time we go down a level, we cut our data set in half that we're looking at until we finally come down and say, okay, it's because of these 3 blocks that had different hashes, and so we'll exchange the partitions that those blocks represent. So this works really good at cutting down on the network bandwidth required, like I said, because we only transfer the trees and then any inconsistent blocks. But as my data set grows and I continue to repair, my time to repair grows linearly with the amount of data that I have, because every time I'm rebuilding that Merkle tree from scratch. And so what we said was, it doesn't make sense for us to keep repairing this data that we've already repaired over and over and over again. So what we'd like to do is just repair data that hasn't been repaired yet, and build the Merkle tree from that, and then use that to just synchronize that set of data. So the devil's in the details. Do I have one more slide? Yes. The devil's in the details because of a number of things. The big one is for level compaction, because what we need to do this, we need to keep 2 pools of SS tables: the SS tables that have been repaired and the SS tables that have not. And so for level compaction, where I want to have exactly 1 partition per level of each set of data, then splitting that into repaired and unrepaired, does that mean that I have 2 sets of levels? So we had to work through some of these problems. What we decided to do was just like we do size tiered compaction as a subset of level compaction, when level 0 gets too full and too far behind, we're also going to do size tiered compaction on unrepaired data. So the advice is going to be that you should be running repair nearly constantly in 2.1, rather than in the old world, try to repair once a week or so. So if I'm repairing almost constantly, then that set of data that I'm performing size tiered compaction on is relatively small, and we can say, okay, we're okay with having a small amount of size tiered going on as long as the bulk of my repaired data over here is nice and leveled. There's actually some implications for size tiered compaction as well that are maybe a little more subtle, because what if I tell size tiered compaction, go ahead and do a major compaction. I'm done with you. You're not compacting adequately enough, so I want you to just make one big SS table of everything. Well, what if I have some data that's repaired and some data that's not? So what major compaction will actually do now is it will look at the set of repaired and the set of unrepaired, and whichever is bigger, it will combine that set into a single SS table. The idea, the reasoning behind that is, if I am upgrading from 2.0, then at first I'm going to have this large pool of unrepaired SS tables. So that's probably what you want me to compact if you tell me run a major compaction. I think that about covers it. There's some implementation details of when I repair and when I tell Cassandra to repair this range of data, and that range of data is part of an SS table, we need to split that SS table apart, and so we anti-compact it into a repaired part and an unrepaired part. But conceptually, I think we covered it. So the other thing is that if I lose a physical disk or a physical machine, then I need a way to repair the data that was already repaired, because hey, that replica that I repaired it with doesn't exist anymore. So the recommended solution, if you're in that situation, is to rebuild a new node. Just take the old one and either replace address. You can say node to replace address, and that says that the node that had that address is being replaced by that IP address is what it's talking about, will be replaced by this new one. That's the recommended solution, because then Cassandra knows, hey, this new one that I'm rebuilding to, he doesn't have all his data yet. We'll wait until the rebuild is complete, and then we'll let him start serving reads. But it's also legal to just say, hey, here's a new node. I brought it up with the same IP address. As far as the cluster is concerned, it's the same node, except it doesn't have any data on it. And in which case, I want to have a repair mode that will rebuild it, without paying attention to, I had this set of SS tables that I thought was repaired. And so there's a flag. I don't remember what the name of the flag is, but you can say repair with this flag to rebuild everything, without respect of whether it was repaired previously. So we've been doing some performance work in 2.1 as well. One of the big factors has been reducing the amount of memory we use in the mem table, because if we use less memory in the mem table, that means that we get to write more data out to disk every time we flush, which means that we're ultimately going to have to do less compaction activity. So far, for beta 1, we've cut the memory used by 40%. We have patches that are being reviewed now that cut it down to about 85% of what the overhead was in 2.0. So we're looking at about 50% better write performance from this, but we're going to do more performance testing after beta 2 and after we address the hiccups that we have currently in beta 1 that I showed you at the beginning. So 2.1 is actually a pretty cool release. I'm really excited for how many long-standing problems we've addressed here. So we've had this feature called a row cache, which in CQL terminology would be better called the partition cache, because it caches entire partitions worth of data. And if you're thinking, holy crap, that sounds like a terrible idea, then you're right, 99% of the time. Because when you're pulling in 100 megabyte partition worth of data, that does terrible things to your memory usage and to your latency. So what our initial plan was to say, okay, let's just get rid of the row cache and replace it with the query cache. But let's make it a query cache that doesn't suck, because MySQL's query cache kind of sucks. And it turns out that the reason MySQL's query cache sucks is that it's really hard to write a good one. So we said, okay, let's put that on the back burner, and let's just fix the row cache so it's not so broken. So what we do is we cache, basically we cache the head a partition now. And you can tell it how many rows per partition you want it to cache. So if I have, if I have a table like this, so what I've tried to imagine here is what Instagram's activity table would look like. They actually did an interview with Planet Cassandra last year about replacing their activity storage with Cassandra. Really interesting interview. But the idea is that I'm going to have a bunch of notifications, and there's going to be some notification source. It might be a photo that says somebody liked this photo or somebody commented on this photo. It might be a user. It might be a notification that, hey, your friend, Jonathan joined Snapchat and here he is. Say hi to him. And then the activity text itself of what happened on that source that you're being notified of. So we're going to cluster the partitions on the notification ID, and in particular, it's going to be a notification ID in descending order. So notification ID, remember, is a time UUID. So I'm saying I want the partitions to have the most recent data at the beginning of the partition. And so then this is how I use the new row cache. As I would say, caching rows only, or I could say caching as all if I want to keep the key cache enabled, which is actually probably a good idea, but in this case I went with rows only. And then here's the new setting is rows per partition to cache. So you can actually set this to all, which is the old behavior, but far more useful is going to be to give it, here's the number of rows that I'm going to need for most of my queries. And so if I have a table of notifications here, and Nick's a popular guy, he's got lots of notifications, and if I've defined my rows per partition to cache to 3, then the 3 first rows for the Nick partition are going to be cached. If the R. Branson partition is hot as well, then the first 3 rows of that are going to be cached, and so on. And so whenever I write a query that says select star from notifications where target user equals Nick, order by notification ID descending limit 3, then that's going to hit the cache. It's not going to have to scan the SS tables and merge the data together. Yeah.
Does it still invalidate entries on writes?
Yes. So it's basically the same row cache that you know and love, except that it has, this limit of how many rows I'm going to cache that caused most of the bad behavior in the past. So we've talked about changing how the row cache works and not invalidating it, but combining it with the mem table writes. And we're not doing that for 2.1. We're just going to fix the main problem, and then we'll look at doing some more optimizations for 3.0.
Is it always going to cache the first n rows of the partition? So
yes.
that time series
yes,
is important.
It's always the first rows. So 2.1, the beta 1 is out. Beta 2 in a couple weeks. And then we're looking at doing release candidates in March, and when the stars align, we'll have the final release. But probably by the end of April is probably a realistic time frame. Final questions. Oh, and reminder that Tyler's giving a talk next week. Nick mentioned this, but I don't think he mentioned that the reason for this talk is that the Python driver is generally available, and come learn all about writing CQL queries in Python. So yeah, last questions.
The query filter or the query cache, was it something more than just a bit filter that you were trying to implement that then afterwards decided not to go that route?
Yeah, I mean the query cache would have been whatever query you handed me, whether it was doing index lookups or any query that you gave me, I should remember the results for that and use an LRU cache on that. And yeah, it got messy and the performance benefits were not clear because to do that kind of query caching, you have to basically turn the query into some kind of key that I can look up in my cache. And yeah, it got messy.
Kind of a side question with the dynamic sizing of the bloom filter stuff. You said you're within 5%. Do you pad that, or do you, in your slide, the bloom filter looked a little too small? Do you go under the false positive? Sorry, over the false positive?
Well, it could be 5% off over or under.
Okay,
so
yeah.
we actually
just go with that size.
We just go with the size it gives us, and maybe it gives us slightly worse performance, but we're okay with that. Thanks, guys.
Thank you.